Okay, welcome back. Hello, everybody. Let's get started. All right. So how was practice lab 2? Did anybody start already?
Yeah.
Yeah? How is it? Okay.
That one took 2.5 hours. I was not expecting because when you said it was going to be short.
It is short. This is super.
Your alarm went off to be right. To be honest, like really dumb. And then I replayed it and I forgot it was there, so I was scared twice.
You were scared of my alarm? Come on.
Yes.
This melodic sound is like, this is how I wake up in the mornings. You gotta be alerted.
I can't hear alarm sounds during the day.
No?
Yeah, that's my morning alarm. Yeah.
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 So, okay, now, but practice lab 2 is an important lab. So this is good. So I hope we get a handle on it. If any problems posted on the discussion board, I didn't attend to yet. So always kind of follow up. If I don't respond to anything on the discussion board, please follow up with me. I try to be responsive, but sometimes I miss stuff. Gets an increasing problem. Good. So we are on module 14. Practice lab 2 is due on 11/14. That's end of this week. We're gonna do today. We're talking about single sample t-test. As you may imagine, a very important topic and a really fun topic actually, because now we're moving away from populations. We don't need the standard deviation anymore from the population. So now it's getting exciting because now we're actually going into sample statistics. So practice lab 3 is going to be coming out on 22nd. I'm going to push the due date a little back because of Thanksgiving. I guess you're all going to go home to some extent. Yeah.
Do you have class on that Wednesday?
Yeah, why not? No? We don't?
Can we do Zoom? Yeah, can we just Zoom that way? It's like, we can go home.
Yeah, good point actually. So when are you leaving in January? You're probably leaving the day before, you're leaving the day off?
Wednesday. People start leaving Monday,
Okay, good. Okay, let me look into this. Yes, it makes sense to kind of do the Wednesday, either remote or we're going to push the whole thing back. Let's see. Let me look into it. I'll get back to you.
How was your race? How was your race?
It went well. It went well. I did under 4 hours. I'm very proud. I'm very proud.
That's really fast.
Well, it was.
How are you feeling now?
I'm good. I'm good. I'm looking forward to my next long run on Saturday.
When's your next one?
My next, I do a half marathon in Sedona in February. Then I do a half marathon in Brooklyn and then a marathon in Berlin next year in September. So.
Do you have to win a lottery to get into the New York Marathon?
No, it was a fundraiser.
Oh, okay.
I fundraised. No, I was a fundraiser for the National Kidney Foundation because of the research in chronic kidney disease and yeah. It was hell of an experience. Like, I don't know who of you is a runner. Like New York City Marathon, like it's the best. It was really great experience. Absolutely.
Your first time doing it?
It was my first marathon, yeah. I did.
Marathon ever?
Yep.
And you did it under 4 hours? Wow.
Yep.
How long were you in the club? How long were you in the club?
I trained 4 months. I trained 4 months every day running and yeah, 60 miles a week.
How much do you run every day?
Yep. Well, the minimum is the minimum of 4 miles a day.
A day? And
But I'm running 4 miles a day since 5 years, 6 years now.
But 2 rounds a day is not really sweating. How many miles are not 20? How many are in the marathon? 20?
33,000.
20?
33.
30?
33,000.
Miles?
No, the whole marathon. No, 33,000 ran the marathon, and the distance is 26.2 miles. Yeah. So it's the distance. It's the distance from a marathon in Greece to essence.
Nah, oh yeah, 26.2, right?
26.2.
But there was a runner that had to run something back, right?
So the story is that the Battle of Marathon was the Athenians defended Athens against Sparta, who meant to invade the city. And the Athenians actually had a smaller army, but they defeated the Spartans. And full of joy, one soldier was tasked to run back to Athens to announce the good news on the marketplace. He ran back with armor and all his gear and announced the good news on the marketplace and broke down and died. Yes. So in his memoriam, they started, and for the first Olympic Games in Greece, they had a marathon run, and that kind of propagated in our times. So yeah.
Do you celebrate Thanksgiving?
Define celebration. I'm gonna have a turkey somewhere. I'm going for a 5K turkey run on Governor's Island. So
you're doing another run?
Yeah. That's what I do. I run into stats.
That's really fun.
No, I do fun things too. No, but yeah. So no, it's I do a turkey trot, and yes, I'm gonna have turkey. But yeah.
Is this next run for another fundraiser? Or?
No. This is just a fun run with a friend. So yeah.
If you did the marathon, you get like 3 things. If you show your medal and like randomly look at Tommy, if you do something, they'll make you a free cookie.
I did not know that.
Yeah. Do you have it on you?
I do not.
You can basically live in a year for free. It's honestly not worth it. Especially with your run.
Okay, I keep that in mind. Gonna flash the medal whenever I get someone want a cookie.
You walk around with it, and like, you know how they were doing the cakes.
Well, no, it was nice. It was the day after I actually went to the park. There was the New York Roadrunner Fair, and it was nice. Like people congratulating you on the streets, so they know that you're anything. No, it was beautiful, really beautiful. Yeah. Okay. T-test. I get carried away talking about the marathon. But again, somebody of you is a runner, please absolutely.
You're like running, you're not 26.1.
Well, it's a stepwise process, right?
I'm the all right there. Would you ever do a triathlon?
No.
Why?
I'm a terrible swimmer. I'm a scuba diver, but I'm a terrible swimmer.
You do that?
Yeah.
Whoa. Really cool. How do you do that? How do you do like you just decided to say, yeah, like, I don't know where to school that. That's it.
Okay, recording now. So we're talking today about the single sample t-test, and this is a wonderful test that actually allows us now to do hypothesis testing without needing the standard deviation population. As you remember, we need to test the difference of a sample, of the mean of a sample to the mean of a population. We do need the mean, the mu of the population, and we need the standard deviation from the population. And we use the standard deviation of the population to estimate the variability of the means, of the sample means of these randomly and independently drawn samples from the population to estimate this mean from the sample and the distribution of the sample means for the purpose of comparison to the population mean. This is hypothesis testing. We want to test this to see whether this sample and the distribution of that sample is different from the actual true population mean. And we will only accept a probability value that the sample we have drawn is from a different population, from a different part of the distribution as the population distribution with a p-value of 5%. Once this is less, we accept it as significantly different from the population mean. Otherwise, it's just drawn randomly due to pure chance from the normal population distribution. 5% is this p-value. So now what can be done? And this is essentially now where we start to think about the so-called t-distribution. And this comes back to an interesting conversation piece, because this t-distribution is basically the basis of all statistics. You will find the t-distribution in the context of so many statistical tests and so many statistical analyses that you will see throughout the time and your scientific careers moving forward. You will see t-scores in multiple regression. You will see it in ANOVA analyses. You will see it in all contexts. And this t-distribution has, hi Eden, I just saw you joined. So the t-distribution was essentially discovered by Sir William Gossett, aka Student, in the 19th century. So the problem he had, and he was the chief brewer of Guinness, of the beer. So they had the problem that they needed to do quality controls on their beer. So you have like this whole massive amount of beers that are being brewed and filled into bottles, and they need to make sure that they have the quality always at the same level. So now you can't test the entire sample of beer, the whole batch of beers. Like, this is too much beer that you will need to test, and you need to discard it afterwards. So they developed and they worked on a statistical method, and Gossett came up with this method to take samples from the overall batch of produced beer. They took little samples and they developed a statistical approach to test the quality, and back from this quality of the sample to see whether it was significantly different from what the quality should have been. So they estimated the variability of the quality from that small sample. And we're doing the same thing. We have a sample, we're drawing a sample from a population, we're estimating the mean, we're comparing this mean to the population mean or to a second sample in the following, but with an estimated variability from the sample and not from the population. So this is a huge difference, because now you don't need to know this sigma, and that makes a difference. So if we have now a normal distribution, and you see the normal distribution here, the beautiful normal distribution in blue on top, and you see the t-distribution. Again, the normal distribution is a function, and I have given you this function. This is an arithmetic function that has a certain shape and a certain form. It's unimodal, symmetric, and bell-shaped. So now with the t-distribution, you mean to approximate the normal distribution. So it has the same shape, it's a little wider, and you try to squeeze it down. So here you have a t-distribution of two individuals, and it's essentially, it's a little narrower, it has a different shape, but it resembles the normal distribution. And this comes again back to the central limit theorem, where we said that larger the n, the more likely your distribution will resemble a normal distribution, because once you go up and you have 2, 8, and 30, it becomes more and more resembling a normal distribution. So the t-distribution means to resemble a set or normal distribution. And this is the underlying principle with it. So there's a little mathematical adjustment to make it look even more than a normal distribution. We're getting to that in a second. So this is the idea. You resemble the normal distribution and you estimate the variability from your sample under the assumption that this is the same variability as you find in your population. So sample size, when the sample size increases, S approaches sigma, and T and Z become equal, meaning it resembles the normal distribution, the variability is the same. The T distributions means to allow you to estimate again the distribution of the sample means for the purpose of comparing the sample mean to either the population mean, as with the single sample t-test, or to any other value. Like you could hypothetically also compare it to any arbitrary value. Yeah, you can say, okay, so I have a sample and I want to test whether the sample is now, because now you don't need the standard deviation anymore from the population. You have this standard deviation of the sample. You can say, I want to test whether this sample is now different than any random number you essentially want to compare it to. Like blood pressure, you draw From a group of hypertensive individuals, you draw a sample of 30 individuals and you're testing their blood pressures, you're measuring their blood pressures, and you want to compare it to the value that is considered to be somewhat normal, which is 120 millimeter Hg, and you compare it to that value. You can do that as well. That's a single sample t-test. So again, so you get the standard deviation from your sample. You're using the standard deviation to estimate the distribution of the sample means for the same purpose as with the set distribution. So if you remember now, the standard deviation from the population, we have calculated by calculating the deviations, squaring the deviations, summing them all up. This is what the epsilon means. We're summing all the deviations, all the squared deviations, and we get the sum of squares. We're dividing the sum of squares by the sample size n, we get to the variance. We're employing the square roots to the variance, we get to the standard deviation. What you're doing now with the standard, that was loud. What you're doing now with estimating the standard deviation from the sample, you have a sample mean, you're subtracting your individual, you take your individual scores, you're subtracting the sample mean, you square it, you sum it, you get the sum of squares, you divide it by n-1. Because you need to account for the fact that your t-distribution is not exactly matching this normal distribution. This is why you, instead of the sample size, use a slightly altered kind of estimate, which is the so-called degree of freedom. So you divide the sum of squares by the degrees of freedom, and you employ the square root, you get to the standard deviation. Yes, Evie?
Can you explain the numbers example why you subtract 1?
Once again, -1.
Yeah, why do you subtract 1? Do it using example.
So, well, good question. Wait, hold on, just a second. Are we discussing this in this topic here? No, we're not. Okay. Okay, I was hoping they would have an explanation of the degrees of freedom already here. So they needed to adjust this. And they needed to account for the fact that the variability was slightly higher in the t-distribution, so they needed to squeeze it. So the idea behind it is now that they use, instead of the sample size, they use the so-called degree of freedom. And the degree of freedom, that's a definition. The degree of freedom is the number of entries on the way to calculating the sum of squares. So sum of squares is this part, right? This is your sum of squares. So you have the sum of squares and you have the list of individual entries. You know your sample mean. When you have your sum of squares and you have all the entries, you can drop one of your individual scores. You don't need that one. You can drop anyone. And the number of individual entries that you can drop is what you're subtracting. And this is a definition thing. Because if you have two groups, for example, and you do a 2-sample t-test, which we're going to do next week on Wednesday. If you have a 2-sample t-test, you're actually subtracting 2. For each group, because you have 2 sum of squares, for each of them, you remove 1. And you can drop one of these. And this will haunt us. This will haunt us down to the ANOVA, where we're doing the same thing. But it's a definition. They kind of settled on a degree of freedom as an arithmetic definition in statistics. And you will hear this a million times down the road. So this is the degree of freedom. I was hoping they're going to explain it now. It's essentially the way you have to look at it. It's basically, let's say you stand with your car in front of a traffic light. And you're not looking at the traffic light, but you only ask your co-driver, okay, can I drive? And your co-driver tells you, no, you cannot drive, it's red. then the traffic light switches to, okay, that's the European system, switches to yellow, and you basically, you're looking at your co-driver. Can I drive? The co-driver looks at you. No, you cannot drive, it's only yellow. Then it switches to green, and then your co-driver tells you, drive, and then you drive. You don't need to know it's green at this point, because it's a resultant of the instruction that you drive. And this is when you have the sum of squares, because the variability is given based on your data, and you're calculating all the means except for that one that you can drop. Just for the sake of redundancy, you take it out. This is the definition of the degree of freedom. Okay? I hope that made sense. I like the traffic light. I like the traffic light analogy because it makes it kind of obvious. It's a resultant, and based on this resultant, you can drop one. Good. Population standard deviation, sample standard deviation. You estimate it, you don't need the population standard deviation, which is hard to get because you can't measure everybody in the population. Therefore, you're estimating it based on a sample variability. Good. Estimating the population standard deviation, we have done that. We calculate the sample mean. We use the sample mean in the corrected standard deviation formula. That's actually, it's the sample population. I gotta change this. So again, sum of squares divided by degrees of freedom. We talked about it. Should we calculate it? Do you want to calculate it through? Yes. All right, let's do it. So, and I have here the example. Okay, so let's apply the new formula for standard deviation to a familiar activity, multitasking. Employees were observed. So this is the example here from the slides. Employees were observed at one of the high-tech company for more than 1,000 hours. The employees spent just 11 minutes on average on one project before being interrupted. Moreover, after each interruption, they needed an average of 25 minutes to get back to the original project. So maybe the reality is that multitasking actually reduces overall productivity. I don't know whether you know the problem, but it's well established that when you get emails in the background of your workday, or you get text messages, you're going to be distracted and it's going to take you ages to get back to your work. So in terms of productivity, studying, turn your phone on do not disturb and then dedicate 10 minutes of an hour to go on Instagram or text with your friends or do whatever. You're going to be more productive and you're going to be more efficient in your approach than when you have it on all the time. Trust me on that one. Good. Suppose you were a manager of one of these firms and decided to reserve a period from 1 to 3 in the afternoon during which employees could not interrupt one another, but might still be interrupted by people outside of the company. To test intervention, you observe 5 employees and develop a score for each time spent on a selected task before being interrupted. Here are the fictional data, 8, 12, 16, 12, and 14. In this case, we treat 11 minutes as the population mean. So what do we have? We have a population mean. We do not have a population standard deviation. For the quizzes, you do not have a standard deviation. You do not have a sigma. You're thinking t-distribution. There's a population mean. You do not have a population standard deviation. Think t-test. The tricky part for the finals, and I'm flagging this right away, the tricky part for the finals is going to be what you need to do if you do research out there in the real world. You need to figure out what test you're going to use with the data you have at hand and the research question you want to pursue. So this is where reality is coming in for you, because at the finals, you're going to sit there and you need to know which method you're going to employ. You do not have a standard deviation. You have a population mean, but not a population standard deviation. You think t-distribution to compare it. And this is what you have here. So we're treating 11 as our mu. What do we need to do next? So the mu is 11. What do we need? We need the sample mean, right? What is the sample mean? So that X bar. So the sample mean is easily calculated as average of 8, 12, 16, 12, and 14, right?
I'm confused.
Why?
Okay.
What confused you?
Where's 11?
Here,
Why is that the calculation?
because they're saying that.
Why? They use those 5 points.
They're saying it. And so according to Mark, Gonzalez, and Terry's, the employees spent just 11 minutes on the version 1 project. This is where it's coming from.
Yeah.
Again, final project. They're gonna pack this. Make sure to do the sample quizzes and make sure that you know how to read the questions. That's gonna be key. Good. And this is, you remember how you asked me whether it's cumulative or not? That's why the final is cumulative, because this is what I want you to learn from this class. I want you to know how to employ that stuff and how to find the right test that you're doing. That's the idea. Okay, good. And you're welcome. Okay, x minus x bar, right? X minus x bar gives you the deviation. That is x minus x bar. Now you want x bar, x minus x bar square. That is now our deviation squared, right?
You mind them?
Yeah, I'm zooming in. Okay, Shana, you indicated that you were interested to look. So you basically have data. You go to each cell where you want to do something with any random data point, right? So this is B3, this is this one. So you basically, you look at it and you try to determine the cell, and then you tell in the cell, you write up there what you want to do with these cells. You're writing up a formula. And here it's B3, that's this guy, minus F2, that's here. And now the only thing you need to do, and this is my locking in, where you put the dollar sign on it. And now you basically, when you drag this all the way down, it will keep the same F2, but it rotates through those that you didn't lock. So it will take the X corresponding with the line you read. So that's how you pull it down. And when you do now the same thing here with D3, you can pull that down. You basically use squaring that. So this is the sign for squaring that cell. Yes.
How did you get the x minus x bar again?
The which one?
X minus x bar?
X minus x bar is B7 or anything in the B column,
Yeah.
minus F2, locked with the dollar sign. Yeah. Go through the spreadsheets that I've posted. Make sure you study those. The formula are not that complicated, and as long as the concept is clear, you will surely understand the formula. Just play around with it. Nothing can happen to you. So this is it's a lot in Excel R. It's just playing, trying things out, and just investigating. You'll figure it out. You'll see. Okay, x bar minus x bar square. What is next?
How do you drag it down?
Hmm?
Sorry, how do you drag it down again? If you double check the pointer, yeah, it's but mine are all the same, and I didn't dollar signs
Yeah, if you go to the right lower corner.
before the letter and the number, right? Yeah.
Yeah. Good. So now we're doing this beautiful Greek letter. We're doing an epsilon. That means we're summing the whole thing up. Did it work? You go to that little thing here, where it changes the form of the cross here. When it gets solid black, then you can drag it. So if we sum this now all up, What is this now? What's that number? 35.2. What is it? That is the sum of what? Yeah, and these are the squared deviations, and that is the sum of squares, exactly. Abbreviated as SS, it's the sum of squares. You will find it quite often, and it will haunt you. Every method basically will have a sum of squares involved to some extent. It stands for variability, and it's part of quantifying the variability. So if we have the SS and we're dividing now the sum of squares by the sample size, which is count of our individual entries. Oops. Yeah. That's still right. 12.4, no, that's not right. Why is that not right? 12.2, oh. Okay, yeah, this would be the variance in a population. This would be ST population. So, but we are not doing that. We're calculating ST of sample. And this is this divided by count of these 5 entries minus 1, right? Degree of freedom, 8.8 doesn't have right in it. Oh no, 8.8. This is the variance calculated from the sample. So you see what the difference here is, right? The population was smaller, but now you're opening it up a bit. And you get the sample closer to the population standard deviation. So you are dividing it, the denominator gets smaller. By that, the variability gets wider. And you're accounting for the fact that in the population, you have more outliers and the variability is going to be larger. So you're trying to kind of add to this variability artificially. Yes, Amira, you were first.
What's the formula for this?
It's this formula.
No, what was it in the thing? What is the text?
This is D9. So it's exactly. If you do not subtract the 1, you're getting to a population standard deviation. And it's the same thing. Also be careful whenever you do the standard deviation in Excel, the default standard deviation is a population standard deviation. Okay, that was too early. So square root of this is now the standard deviation, right? So we know that.
Can you go over the standard deviation operation formula again?
Yep, just in a second. SQRT of this. 2.996. This is not this. This is stdef.p. Okay, so just in comparison, this is the one for the population. This is the one for the sample. So you have ST population is calculated as D9, which is our sum of squares, divided by the count of all individual scores. So you're counting the scores, that's 5. You get to the population. You're subtracting 1. You're subtracting that 1 that you can drop from your individual scores, and you get to your sample standard deviation. Or variance in that regard.
Oh, and the second one, you do the same thing, except you subtract 1.
Exactly. Same formula.
And wait, what do you need parentheses? Because when it mess it up.
Yeah, with parentheses, you got to be careful.
You put it outside.
Parentheses, always think of the number one mathematical rule. You always have division comes before subtraction, right? So you need to put the subtraction inside of the parentheses. If you don't do that, you're dividing it first and then subtracting one. And that's okay. So they are now logically. So that's a good mistake. When you do that calculation, you got to distinguish between the standard deviation population and the standard deviation sample. You need to know whether you're doing a SAT test or a t-test. That's source of error number one, which you're losing points that you should not be losing. Please don't. Point one. Point two, this is the standard deviation. Because if you want to calculate now the standard error of the mean, you're doing this. You're taking the standard error of your sample, which is 2.966, the standard deviation of the sample, and you're dividing it by the square root of the n. So this is your standard error. The important thing to keep in mind here, and this is the next source of an error. Please don't do this error. Don't make this mistake. There's no subtraction of a 1. And both for the SAT test as well for the t-test, you're not subtracting 1. Good? Okay, so there's a question from Eden. Oh, okay. Okay. I hope that's all clear from you, Eden. I have the speakers on. In case you have a question, raise your hand or say something in the microphone. Okay, good. So we have standard error of the mean now. So what do we want to do?
Yeah. How do you get standard error?
Well, you're dividing it by the count, the square root of the n. Square root of the count. Yeah.
Oh.
Mm-hmm.
Yeah.
Yeah. Good.
Like 1.32.
It's 1.32, correct. 1.33.
Yeah.
We're rounding up. Good. Okay, so this is this. This is now the standard error of the mean. This is this. So please, standard error of the mean always divided by the square root of the n. No n minus 1. That's just the standard deviation, sample standard deviation. Okay, so now we're doing the t. So what is the t? It's x bar minus the population mu. It's 12 points. So this is now the t. T equals this minus mu in parentheses divided by standard error of the mean, 1.06. Okay, he says 1.05. This is not 1.05, but it doesn't matter. All right, we ignore this. So 1.05, is that significant or not?
Yeah.
Yeah. It's 1.96 on the normal distribution, but now unfortunately I have to do something else to you, which you're not going to like, because I'll make it a little bit more complicated because we're not using the SAT score table anymore. We're using now the t-score table. Because of the change in distribution and the change in variability, we're now looking at a different table. So the interpretation is a little bit different. So this one is considerably easy to read. So this is again from Open Intro, from the book Open Intro. So I personally find this one fairly intuitive. So first of all, you need to know whether you're looking at a one sample t-test or a two-sample t-test? If you have a two-sample t-test, remember you need to take into account both tails for a two-sample t-test. 99% of all analyses will be a two-sample t-test. You look for a two-sample t-test, you're looking for 5%. You're looking for your degrees of freedom, which is, what is the degrees of freedom for our working place example? What? Okay. The degrees of freedom. What's the sample size of that example that we did?
Where do you find it?
Well, the sample size. How many scores did you have? 5. Exactly. What's the degree of freedom? Sum of squares. And you can drop 1 from the scores. You have 5. How many can you drop?
1.
Exactly. So what is the degree of freedom?
4. 4.
4, yes. So 4 you have here. You find 2 tails. Your critical value here is 2.78. If your t is smaller than 2.78, you are not rejecting the null hypothesis. Only once you exceed this critical value, then you're rejecting the null hypothesis. Okay? Everybody with me? Okay, that was the example. So what do we conclude now from that? Does the intervention work or not? Did the intervention make a significant difference in the sample mean or not? No? Exactly. So the intervention was not effective. Exactly. That's the conclusion. So based on our sample, so that would, so also it's important that you know how to essentially express your conclusion. So based on the sample at hand that we have studied, we do not reject our null hypothesis that there's no difference between those employees that were subject of the intervention compared to the population mean. So avoiding shielding employees from interruption does not make a difference, which I contest, but that's a different conversation, please. Okay. So that's a single sample t-test. It's single sample because you only have one sample. You take the degree of freedom instead of the sample size for the calculation of the standard deviation. That's the only difference in the estimation of the variability. Then you use the standard deviation to estimate the standard error of the mean, which is the distribution of the sample means, the variability. And you use that for hypothesis testing to calculate your t. That's the t-table. You do again the 6 steps of the hypothesis testing. You identify your population, your distributions, you make your assumptions, and it's important that you map those out, that you know what the mu stands for, what the x bar stands for, what the sample was, what the intervention was, because that will help you to express your conclusion based on your data. Then you determine the characteristics of the comparison distribution. You determine the critical values with a degrees of freedom of n-1. That's 4 in our case, right? So the 2.78, that was our critical threshold. Then we calculate the test statistics, which we did. 1.06 is our t-score, and we make a decision, and we express our conclusion. Okay? Easy, and really super valuable. Super, super valuable. Okay. So now we're doing another example. So we are now looking at another single sample t-test. So we have clients at a counseling center and they're signing a contract to attend at least 10 sessions. So since you all, or many of you are prospective psychology students and psychologists, if you want to convince somebody to change behavior, this is very complicated, right? People don't want to change the behavior. So what you do for that, psychologically, you can approach them and you make it visible to them that they have agreed to initiate a change in them, and you make them sign a contract with themselves or with the psychologist. I don't know what different models out there. So, but they're signing this contract. So we have population 1, they're signing a contract, and you have population 2, they're not signing a contract. So now you have a comparison distribution, which is population distribution of the population means, and use a single sample t-test because there's one sample, and we know the population mean, but not the population standard deviation. So the assumption is now that both samples are equally distributed. And we are now assuming that mu1 and mu2 is under the null hypothesis identical. Whereas the research hypothesis is saying that they're not identical. So now we have the characteristics of the comparison distribution. Now we're going back here to this. So this is now our X. The number of sessions that entered by clients reported the mean. So, okay. So the mean by Hatchett in 2003 was 4.6 sessions. That's the mu. That's this example here. We have 5 students signed a contract. And so the population mean they're not signing a contract. So now they have 5 students that sign a contract and they're hoping there will be an improvement. So now they sign the contract and later on they attend 6, 6, 12, 7, and 8 counseling sessions after signing the contract. The researchers are interested only in their university, so they treat the mean of 4.6 sessions as a population mean. So this is the mu. What are we going to do first? What do we need?
We need the X bar.
Yes, exactly. So X bar, we're doing average of this. Perfect. What are we doing now?
And then you need the other formula we used before.
Exactly, yes. And what are we calculating now? Yeah. Okay. We're calculating. Oops. It's realistic. Okay. So you're calculating the squared deviations. You calculate the difference from your individual entry minus the X bar. Don't forget to lock it in. And you square it. And once you square that, you drag it all the way down. And you build the sum. That is the sum of squares. Now you calculate the variance. The variance is this divided by. What are we dividing it by? Yeah.
Wait, you're doing the variance
Yes.
divided by. You're doing a count function?
Yes. What are we counting?
X.
And what else do we need to do? You need to subtract 1 because we want the decrease of freedom, right?
I'm confused about different like formulas and things that we use.
Okay.
When to use which.
Okay, so once again, sum of squares.
Yeah.
Sum of squares divided by the degrees of freedom gets us to the variance. Square root. Square root of this variance gets us to the standard deviation.
Okay.
Good. So what's next? We want the standard error of the mean, right? How are we gonna get this? That's so interesting. I remember when I was a student and there was a question I couldn't answer, I would always look at my book and I wouldn't look at the teacher's eye, right? They're like, that's the first time I'm standing here and I pay attention to it. It's like, this is really a thing. It's funny. Okay, Marcela, what am I going to do to calculate the standard error of the mean?
Oh, God. Oh.
Don't talk to me.
Wait a minute, I think I know.
Okay.
Is it S? It's S divided by the square root of n?
Yes, bingo. Yes, you got it. I know you know it. Divided by square root of the n. Okay. Okay, very good. Good. Standard error of the mean is 1.1. Okay. So 1.114. Yep, that's a 4. Good. So that's the standard error of the mean. We've calculated same numbers as Norton and Heinzen. What are we doing next? Amira? No? So we need a t-score, right?
Wait. So,
I have to do this more. It gets my movement in this. Okay.
wait, so how are you getting, like, I understand we're putting everything into the formulas that we have, but how do you know which formula to put everything into and when to put it in?
So now we have the standard error of the mean, right?
So why is that what we have now? And why is this the word that we're going?
Yeah, we need the t-score now, right?
Yeah.
We just did that on the other spreadsheet. We calculate the t-score by calculating the difference. Remember? And dividing it by the standard error of the mean. This is how we do hypothesis testing.
Right.
Yeah. And we're doing the same thing here now. Because we have here a population mean of 4.46 sessions. And we want to compare our sample mean to those 4.6 sessions. And taking into account the standard error of the mean, which is the variability of our distribution of the means around the sample mean. We're doing the same thing. We're calculating the t. We're doing our x bar minus the mu divided by the standard error of the mean. That's our t.
Okay.
So the $1 million question is now, is that significant or not?
So how do we know if it's significant?
You've been in my class for 3 months and now you really ask me that question?
Sometimes it is,
Okay, good. So how do we determine a critical value? How do we determine a critical value? You're looking at me, I see that. Yeah.
If it falls within 95%, if it falls within 95%.
Yes, that's correct. And where would we find that? How do we find that out? We need a critical value, right?
Yeah, find the confidence.
What? Yes, down the road. But what do we need first? We need a critical t. Before it was a critical set, which was 1.96. Now we need a critical t. Yeah. I'm happy you agree. Good. Okay, so critical t we get from the t-score table. What is the critical t? We're looking for 5%, right? What's the degree of freedom? 4. It's the same value as before, it's 2.78. So, but now the t-score that we have calculated arithmetic is 2.87. So now it's greater than the critical t, and now we're rejecting it because it's greater than the critical value. Yeah? Remember, no? Where's the disconnect? No, Amira.
No, I'm behind.
But where are you? Just,
Sorry, so-
we're a small group. Where are we? Okay, that was refreshingly honest. So it's always the same principle, right? You have in set statistics, you calculate a set score. That's all you do. You calculate the difference and you do the standard error of the mean and you divide the difference by the standard error of the mean. Now you have a t-score, you do exactly the same thing. You just do it with a calculating a t and you're comparing it against a critical value that corresponds with a p-value smaller than 5% on a two-sided test. On the set score table, we looked for 2.5%. You remember the negative sets? And that was because we needed to account for everything to the left, assuming that on the right, we have another 2.5% that made it a two-sided test. Here, the t-score table looks a little different because it gives you a priori here two tails with 5%. And now you just got to find the corresponding t-score that corresponds with this threshold, with this critical value. And that's here the 2.78. Okay, watch the lecture recording again. It's really, it's not.
I get this part, I just didn't know what's the part of the question you're asking me about.
Oh, okay, sounds good. All right, okay, so we're rejecting this. This is significantly different. So counseling sessions, having people sign a contract works. And as far as I know the literature, and I'm not a psychologist, it does work. It makes a huge difference. It's commonly used in addiction therapy and all kinds of psychological approaches. Super effective. Okay, so confidence intervals. How are we going to do this? There she goes. So confidence interval. You brought up confidence interval. How am I going to do this? I like this. I gotta get you more. Okay.
Yeah.
Good answer. Okay. Okay, so we had 1.96 on the set score, right? You remember?
Yeah.
We do mean plus minus 1.96 multiplied by the standard error of the mean. Now we're doing the same thing, we're just taking this critical threshold, and we're doing the same thing. We're going on both sides. So this was 2.78. What we're doing, so here, that's 2.78. Now we're calculating lower limit is x bar minus 2.78 multiplied by the standard error of the mean. And we're doing upper limit is x bar plus 2.78 multiplied by the standard error of the mean. So this is 4.7 to 10.9. 4.7, both 4.7 and 10.9. So this is now our 95% confidence interval. Our mean is now significantly greater than the 95% confidence interval, right? So we have this mean is 7.8. The lower limit of the 95% confidence interval is 4.7. Does not include the population mean. The definition of the confidence interval is that we have a 95% confidence that it includes the population mean. If the population mean is not in there, our sample is significantly different. And that's the case here. Yeah? Good. All right. But it's easy, right? It's not.
So easy.
No, but it's not that complicated. It's the same principle, right? You did it for the midterm and you did well in the midterms. Same story, just in T. Any questions? Yes.
I'm a little bit confused still about the degree of freedom.
Yeah.
Like,
I'm looking at the slide
Mhm.
and it says, like slide 15,
Yeah.
it does an equation and the equation is very simple, but I don't see how the graph like reflects.
Slide 15.
Yeah.
So this is n minus 1 is 5 minus 1, right?
Yeah.
So here we have 2.78. So if we look at our t-score table, this is what I did. I just went to the t-score table and I found the critical value corresponding was a two-tailed test of 5%. And this gives me here was degree of freedom of 4. It gives me 2.78. And that's the same thing they did. So they are saying this is our confidence intervals. These are our thresholds. And this is minus 2.78 and plus 2.78.
So how does that, so now I understand how to find the t-test and the chart, but how does that connect with the 4?
The 4.6.
Yeah.
So
No, the 5 minus 1 is 4.
that is the degrees of freedom.
That would be the number that's on the chart.
Exactly. Exactly. This df is the same df here.
Okay.
So you go df 1, 2, 3, 4, 5. So this is a sample size of 2, sample size of 3, sample size of 4, sample size of 5. So this is the sample size of 5. Oops, sorry. Sample size of 5 plus 1 minus 1 gets you to a degree of freedom of 4, and the threshold is 2.78.
So it's saying if we don't know the like 2.78 score, that that's how we find it using the chart.
Exactly.
Okay, thank you.
Yeah, of course.
So this is like the z-square table, but in t.
Exactly.
Okay, so then is there like is there a difference between which one's which besides it's labeled T and one's labeled Z?
Yes, because the set score table was independent of your sample size.
Right.
And that is essentially something, you remember that I always talk about statisticians like a sample size of 30 at the very least. Because once you get to 30, and keep in mind, this is two tails, 5%. You go all the way down, here it's a 2.04. This is considerably, this is getting closer to the 1.96. That's why you get away with set statistics as soon as you have a sample size greater than 30. You are, to some extent, every statistician, this is like when you get like a wink and you can go away with 1.96 instead of the 2.04. But until then, when you ask, and this is another thing, if you're being asked to calculate a confidence interval, you have, for a t-distribution, you have to use these thresholds. You cannot use the 1.96. Only once it's greater than 30, then you can use 1.96. And not even that is true, because the larger the sample size, the closer it gets to normal distribution. And the greater the sample size, the further this critical value approaches 1.96. Here was 500, you're at 1.96. If you go towards infinity, it will go towards 1.96. So this is part of that function, right? Everything is a function. And this bell-shaped curve is following a function. So is the t-distribution following a function. It's nothing else but that. And the greater the sample size, the more it resembles a normal distribution, and you get away with a set distribution after 30, or most efficiently when you have 500. When you do my graduate course, you're going to get a data set where you actually have samples of that's larger than 500. So, okay, so this is this. Yeah, so this is how you do it. You essentially get the critical thresholds. You can employ this on the normal distribution curve, which is not strictly the normal distribution, but you get away with imagining it as such. And you're basically employing the same principles as for the set distribution. And this is the simplest case. This is the single sample t-test. Any questions on that? What's important is that you recognize when to use a set test, when to use a t-test. What's important is that you go when, as soon as you have a t-distribution, that you know how to calculate the confidence interval and that you take the right critical value. These are the mistakes that, please don't do them. Okay, confidence interval, same story, we just did it. We just did the same thing, indicate them. 2.5 in each tail, we did that. Middle 95%. We did all of that. 4.71, 10.9, we did that. Um, Understand? The sample mean should fall exactly in the middle of the two ends. Yes. Interpretation of the sample means yes. Okay, population mean is 95% of all times. You remember this graph where we had this repeated samples drawn? So 95% of all these samples will contain the true population mean. This is the definition of your 95% confidence interval. Equally, you can calculate coherence D for the effect size. Again, your sample size is now calculated in the same fashion as you have done it before with the -1. So this is the same thing, but you do not divide the difference by the standard error of the mean. You take the standard deviation, you get coherence D, and this allows you to quantify the effect size with the same grading scale as we had for the STAT test. So 0.2, 0.2 to 5, 0.5 to 0.8, 0.8 and greater. Okay. Any questions? If not, I guess we're done for today. It's not complicated. It's just really something. Eden, any question from your end?
No, thank you so much.
Once
Did you
again,
hear?
please.
Oh no, I said I don't have a question, and thank you.
I do not
Do you
hear
not
you. Wait, hold on.
No, you not hear me? No, I don't have questions. It was clear. Thank you. Why is it not? I have a problem with my. Oh, no.
Yes, now I hear you.
No, I don't have a question.
No
Thank you.
questions?
It doesn't work with the microphone, I guess. No.
What? What did you say?
No, I
No,
have a problem.
no question.
No.
Not a question. Okay, good. Okay, sounds good. All right, see you next week.
You too. Wait,